Hello, everyone. This week we will talk more about the ERN models. So last week we already talked about Model 1, Model 2, which is sampling with replacement or without placement, but order matters. But in this week we'll talk about models that the order not matters or order irrelevant cases. These are Model 3 and Model 4. So let's review at so first let's see what Model 3 is. We draw at once K balls from ERN with N balls. That is a setting very similar to what we talked about last week. But in this time, we draw k-terms from the ERN with n balls, and the balls are not returned, which means each time they are picked out, and we are not sending them back to the ERN. And the order of the k balls does not matter. So what's the difference between Model 3 and Model 2? The not returning pattern is the same, which means like you remove one balls out. The first time you have n balls inside. The second time you have n minus 1 balls. The third time you have n minus 2 balls, and the fourth time you have n minus 3 balls, and so on. But what does the order irrelevant means? The order doesn't count, which means like if you draw the first ball and the second ball, and the second ball and then the first ball, they are counted as the same event. But previously, if you were like drawing the second ball first and then the first ball, or in another case, like drawing the first ball first and then the second ball, these two cases are considered different. So in this case, the outcomes are no longer list; they become sets because the sets has a property like if it's the order is not relevant of the element inside the set. So the outcome is a set. It's a set of case element, which is A1 to AK, and AI is the number of the ith row. So obviously the cardinality of the set is K. So that's like the number of draws. And each draw can be in 1 to n, but at least it should be a subset, which means no 1 can be the same because the ball is not returned to the ERN. Okay, and the sample space here is we denote as omega. The omega, I think it's omega 3 is not omega 1 because this is a third model, so this might be a typo error. And here, so what's the sample space is? The sample space must be like outcomes. The element of the sample space is outcomes. So the W must be a subset of the original cases, like 1 to n. It has n choices, so it is a subset of that. But the cardinality of the W here must be K. So it's all the possible subsets of the size K of the subset 1 to n. Okay, and so how can we know the cardinality in this case, like the set omega 3? We calculate it as first we remember the cardinality of our sample space 2 is n following k, which means like it's n times n minus 1 times n minus 2 times 2 was n minus k plus 1. So in this case, what's the difference between this model and the previous model? It's just like the order is not relevant. So how we can know the order difference will produce it's divided by k factorial k. So why that's the case? We can make a proof of that. So firstly, I would like to say it's about a small trick in permutation. Like if you treat k as a number from it's a number of draws. Like you draw 2 balls and you can swap them 1 by 1. So in this case, order irrelevant and order relevant is 2 times different. But if 3 balls 1, 2, 3, you can manage at 3, 2, 1 or 3, 1, 2 or like 2, 1, 3. So there's totally 6 case, and that is like divided by 6. But that is also can written as 3 times 2 times 1. So in this case, it seems like a factorial pattern for the permutation. So the strict proof is by using the surjection function. So first we define a surjection map or surjective function from the domain is the sample space of model 2, and the codomain, or we say the range, the outputting domain, is the sample space of model 3. And because previously the model 2 sample space is a tuple, or we say a list from like A1 to AK. And here is just a subset. So obviously, what can we convert a list to a set is just to ignore the permutation patterns. So in this case, we can say then the pre-image of the set A1 to AK, the pre-image of the range are all possible permutations of like A1 to AK. So that is the single difference makes set different from a list or tuple. So we just ignore the permutations, and based on the permutation theorem, already know that if there's like k element inside some set, and we select k of them, which we select all of them, the k is fixed here. So the permutation is k factorial divided by like k minus k factorial, which is 0 factorial, which is 1. So it's just k factorial. So in this case, we can say, okay, the sample space, the cardinality of sample space 3, model 3 is just get rid of the permutation pattern from the cardinality of the sample space of model 2. So we just divide the cardinality of model 2 by k factorial. So that's the end of our proof here. So maybe we will introduce a new definition called binomial coefficient. Binomial coefficient is in a binomial model, which we'll talk about later. And in this case, we'll describe the cardinality of model 3's sample space as binomial coefficient. So first, what is binomial coefficient? So for R belongs to the real number and N belongs to the natural number, we define the binomial coefficient R choose N. So this term reads as R choose N. And R choose N is calculated as R times R minus 1, which is like R following K pattern divided by N factorial. And this is the general formula. This formula is related to like binomial distribution later, so it doesn't really have a sense of what to understand about that. It's just a formula. But if you are very careful, you will find out this is exactly the same as what we looked at before. Is N is like R following K divided by N factorial, which is exactly the same as this. The cardinality of model 3 sample space. So as a result, we can denote the cardinality of this model here, just N choose K, and that's all. But there are some trivial cases, some very special cases in binomial coefficient. So like in most cases, R is greater than N, and they are all like greater than 0. That is typical. But if N equals to 0, we cannot able to think about that. Like what is like we choose some number we choose 0 is nonsense. So in this case, we define it as 1. And if N is smaller than 0, like if we choose a negative number of objects, is even more unreasonable. So in this case, we define it as 0. So N choose K is equal to N factorial divided by N minus K factorial times K factorial, if K is smaller or equal to N. This is the most useful version of the formula, I would say, in later calculations or in later definitions. Why is that? Because what's the difference from this to this definition? Because we separate the following term into 2 factorial, like N factorial divided by K factorial. Divided by N minus K factorial. So in this case, the last term of N minus K is divided out, which always remains here. Like if it's not divided by like N minus K, it will have in this case N is R and K is N, so it's R minus N plus 1, R minus N minus R minus N plus 2, r minus n plus 3. I mean, yeah, I mean, I have a, I would say there's a bracket there. So it's actually r minus n plus 1, r minus n, r minus n minus 1, minus 2, minus 3, minus 4 until it's falling to 1. And if k is greater than n, like we choose, for example, we choose 5 objects from 3 objects, it's not really possible. So we also define this as 0, which is impossible cases. So let's see more about the applicable examples. The 3 cards selected from 52 card decks. So the Model 3 is really helpful in most of the poker card problem. This is a simple one. 3 cards are selected at random from a 52 card deck. What is the probability of the hand of black heart king, black spade queen, and a spade jack? Okay. So first in this question, we'll first consider its sample space. So the sample space is we choose 3 cards, or we do not return the cards, and the order is not matter because who cares the first is king or the second is king. So this is a Model 3. This is a Model 3 example, and so the sample space is like A1, A2, A3, which each AI represent a card from the 52 card deck. So in this case, A1, which is an example we consider, only has one possibility, that is spade K, spade K, club Q, and club Jack. So in this case, this is 1. So the probability of A1 in this case is the cardinality of A1 divided by the cardinality of the sample space, which is 52 to 3, below 1. So this can be very easily solved. And this is usually the simplest case, but we sometimes deal with more complicated cases. Like for this example, 3 cards are selected at random from a 52 card deck. And what is the probability of getting a hand of king, queen, and jack? So in this case, it's not specifically say it's a spade king, it's a club queen or club jack. No, we can say all of the 4 kings are available. So the sample space is still the same because it's still like selected cards without replacement, and all this not matter. So the sample space cardinality is still the same. It's 52 choose 3. However, the event, this is not a simple event. It doesn't consist of one case. It has several possibilities. Like for example, king, we have king spade, king club, king hearts, and king diamond, and all of the 3 has 4 cases. So how can we calculate this event probability? Well, say because okay, the A1 belongs to the set of king, A2 belong to the set of queen, and A3 belong to the set of jack. And in this case, each of the set have 4 members, and we only choose 1 from the 4 members, so it's 4 choose 1. So king has 4 choose 1, queen has 4 choose 1, jack also have 4 choose 1. So we just use the principle of multiplication to calculate that 4 choose 1 to the power 3, which is 4 to the power 3, because 4 choose 1 is same as 4. That is calculated as 4 factorial divided by 3 factorial divided by times 1 factorial, which is like 4 exactly. So this question is very similar to this pattern, which we first calculate the sample space cardinality and then calculate the events cardinality. And in this case, the event probability can be the only part we need to think of differently per question. Always in deck, in poker card deck question, we always use the Model 3. So the sample space cardinality always remain the same. Let's also see another example. 3 cards are selected at random from a 52 card deck, what is the probability of getting a hand of king, queen, and jack with 3 distinct suits? So in this case, it becomes more complex because previously we say we can get a hand of king, queen, and jack, and that's all. But what does the with 3 distinct suit means? So it means like if the jack is a spade, then the queen or the king cannot be spade. It can only choose from the other 3 one. And once we select, oh, queen is a diamond, and then the remaining queen cannot be a diamond or nor a spade we have defined before, so it can only be a club or a heart. So in this case, we'll use a different strategy. The cardinality of the sample space is still 52 to 3, but the sample space, the first we say we choose a jack or queen or king, that's okay, but we choose at least one of the cards. We say it has 4 choices, we choose one from them, so it's 4 choose 1. But for the second card, it only has 3 choices and we choose 1, so it's 3 choose 1. And the last one, the third card, we have 2 choices and we still need to choose 1, so it's 2 choose 1. So we times this out is 4 choose 1 times 3 choose 1 times 2 choose 1, which is 4 times 3 times 2 divided by the cardinality of the sample space, which is 52 choose 3, as we calculated before. These are like the simple process of like card choosing problem, and there can be more complex examples. Like this example, 13 cards are selected at random from a 52 card deck. Verify the following probability. The first question asks like how many possible hands are there. So this is a question asking like how many possible hands is like the possible cases of the 13 cards are choosing from 52 card decks. Okay, this seems like to be a cardinality of the sample space, which is 52 to 13. And after the calculation by a calculator or like software, we get this large number is 52 to 13. And what's the probability of getting a hand consisting entirely of spades and clubs with at least 1 card of each suit? So this question has 2 steps to solve. First one is to consider the probability of getting a hand of card consisting only spades and clubs. That is to say, we only have 26 choices over the 52 choices because the other two kind of like type, the heart and the diamond is not in our consideration. So we only consider to draw 13 cards out of like 26 cards, which is the 26 choose 13. However, it says at least 1 card of each suit will be included. So there's 2 specific cases we need to ignore. That is 13 cards of spades or 13 cards of clubs. That is 2 cases. So we just use 22 choose 13 minus 2, which is over 52 choose 13, which is we calculated before, the sample space cardinality. And this result will get something many 0, and there's 16379 about this number. So there's also another question like what's the probability of getting a hand consisting of exactly 2 suits? So that is not exactly the same as this one, because this one we say our suits is already defined, the spades and clubs. So what about exactly 2 suits? This question asks, I think, so if it were me, I would first think of like exactly 2 suits which means it's not at least 2 suits or at most 2 suits. It means at least 2 suits. So at least there will be 2 suits. They cannot be 1, they cannot be 3, they cannot be 4. So the result from the second term is very helpful because here we say we consist of exactly 2 suits, right? It's spades and clubs, but at least one of the cards in a suit, so it ensures it has 2 suits. So seems like we just need to change the space and clubs into different suits to solve this problem. Like what is the probability of like entirely of diamond and clubs, and that is the same as this result. So the problem is simplified into calculating how many choices for those two suits. So there's only 4 suits, and we need to choose 2. So there's 4 choose 2 probability of getting the suit for all the suit combinations. So the result is 2 times 4 choose 2 to the result here. And the answer we get is many 0, but the same number 0, there's 4 0 after the decimal point and 98271. So if you justify that, this is 6 times larger than the second question's answer. This is because 4 choose 2 is equal to 6. Because we calculate this 4 times 3 times 2 times 1 divided by 2 times 2, which remains like 3 times 2 times 1. So in this case, it is 6 times larger. All right, so seems like we are moving to our last model. It's sampling with replacement or the irrelevant. This is the most complicated model. It's different from you can say, oh well, it's just like it's a slight different from our third model, which only we say we with replacement. So we getting the ball back to our urn after each draw. But the consideration is from different angles. It's not to consider we have K balls or we have N balls, K draws, something like that. We use a different system to record this process. For example, we draw K balls from the urn with N balls. The number of the drawn ball is noted, and the ball is put back into the urn. The order of the ball is not noted. So this is a description of what exactly the model 4 means. The outcomes, so let's first think about outcome. The outcome might be trivial because for each of the ball, it can be more than 1. For example, if you draw the ball number 5 out for the first time and you put back into it, and the second time you also draw the number 5 out, and third time you also draw the number 5 out. So each time you just draw number 5 out. So during some process, it can be the number 5 ball it's not usually 1 or 0. It can be 2, 3, 4 at most the times you draw. So we denote the outcome as a tuple where Ki denotes how often the ith ball was drawn. This means like if you draw the ball numbered 5 times, then K3 is equal to 5. But for considering the whole problem, the tuple value should sum up to K, which means like K1 plus K2 sum up to Kn. They plus together is equal to K, because for each draw, you will draw 1 ball out, and that is exactly 1 ball. So the number of balls totally should equal to the number of draw that you are made before. And the sample space here is it's the omega 4. So this is also a type of error, I think. And this is denoted by the this is a tuple from K1 to Kn, and Ki belongs to some natural number including 0, because if the ball is not drawn at all, it should be 0. So the N0 term means it's a natural number, of course, but it's a natural number union with the number 0. And there's another condition we need to satisfy, is the sum of the terms in this tuple is equal to K. Even though the order is relevant, we still characterize the sample space with n tuple. But consider another way. If you say it's a set, let's say the outcome and the sample space term is a set, it doesn't matter, because set already assume the order is irrelevant. So if it's a set and it's K1, K2 to the Kn in a set, this still makes sense. So use the form that you feel comfortable with. Do not consider, okay, which is better. I think they're just the same with different notations. So after understanding this point, the cardinality of the set omega 4, this can be made into the form like k plus n minus 1, choose n minus 1. And this is exactly the same as k plus n minus 1, choose k, because when we calculate these two forms, the denominator is always k plus n minus 1 factorial. But let's consider the, okay, so previously, I mean the two terms, for this term and this term, the numerator is always k plus n minus 1 factorial. But for the denominator of these two terms, it is exactly the same, because in this term, we say is n minus 1 factorial times k plus n minus 1 minus n plus 1 factorial, which is just k factorial. And in this case, the denominator is k factorial plus k plus n minus 1 minus k factorial, which is n minus 1 factorial. So these two terms, denominator is always k factorial times n minus 1 factorial. So that is exactly the same. So use the way that you think you are is easier for each question, but the result is exactly the same, just writing is different. And why this case is true, we can use an example to illustrate why this seems like reasonable. So suppose that there are k birds perched on n trees, which means birds are indistinguishable and may occupy any number of trees. So there's a different thing about here. So what does it mean? Like birds may occupy any number of trees. It doesn't mean like one bird can occupy any number of trees. Like a bird can perch on 3 trees, 4 trees, or there's a huge bird can occupy the whole forest. It doesn't mean like that. But the first time I saw this question, I think about that way too. So so the correct way to think about this question is like the birds as a group. The birds group can occupy any number of trees. So which means all birds can perch on a single tree, or some birds can fly out of the tree to perch on different trees. It's like a tree birds relation, like one bird can match one tree, or 2 birds match one tree, and 3 birds match 2 trees. It's not defined. It can be any number of trees and birds combinations. But one thing must be sure is that one bird at the least perch on tree, and at most perch on one tree. So for each single bird, it perch one and only one tree. Yeah, it perches on one and only one tree. And all the birds are indistinguishable, so the order is not relevant. So how many different ways are there for these k birds to perch on n trees? So in this question, we'll first think about one idea. We will symbolize the birds by x, and to symbolize the birds on the tree, and we symbolize the tree as a vertical line. So for example, if there's 4 trees and there's 6 birds, and we can say this example, the 4 trees are listed here: 1 vertical line, 2 vertical line, 3 vertical line. So this is the first tree to the left of the first vertical line, and between the first and second vertical line is the second tree. The third tree here is empty, and the fourth tree is the right of the last vertical line. So the 6 birds are separated into 2, 3, 0, 1 patterns. So this is way to visualize what idea we have to symbolize birds by x and the tree by vertical line. And in general, if we have we will have n minus 1 separating lines, the vertical lines, because there's always like one more tree than like we say the boundary between trees, because if there's 2 trees and there's will be only 1 boundary, and there's 5 trees and there's only 4 boundary to separate those trees out. So we'll have, if there's n tree, and there will be n minus 1 separating trees, or the vertical lines here, and the birds, the number of x will be k, which is already set in the problem. So let's talk about the condition here. So we have n minus 1 plus k objects, which means we sum up all the symbolizations, the x, k, and vertical line is n minus 1. So we sum them up is n minus 1 plus k objects. And we need to choose kx out of these n minus 1 plus k objects. So what does this mean? Why we need to choose x out of this n minus 1 plus k objects? So because the trees are already fixed, so we can say that the order of the vertical line cannot change. We cannot say one tree is pre-existed in the first place, and after birds flying, tree also move. That is not reasonable in this question or in any types of the model 4. So the trees are fixed. We are not able to choose the vertical line. All we choose is to select the x out or the birds out and to separate them into correct position. So this means why we need to only choose kx out of this n minus 1 plus k objects. So this is exactly the same as we choose k out of n minus 1 plus k, which is exactly our formula here. So the cardinality of the fourth model's sample space is k plus n minus 1 divide choose k, which is also we can replace k with n minus 1. So this is solved. So after we already explored all of the models, we can make a beautiful summary here. As consider a model in which k times the ball is drawn at random from a urn with n balls. We can remember the first model is order is relevant, and yeah, the order is relevant, and also the we draw a ball and replace it. So this is the first model, and the cardinality is n to the power of k. And the second model is we do not return the ball back, and the order is still relevant, and the cardinality is n following k. And the third model is we do not replace the ball back after each draw, and the order is not matter. It does not matter. It's irrelevant, and the cardinality of this model is n choose k. And the last model is the model we just talked now, and it's the cardinality is k plus n minus 1 choose k. This is a very large binomial coefficient model number, and yeah, that is all of the 4 models we discussed here. And there are many related questions about each model. There's like poker cards question. There's like a painting problem, like to paint a die with each side a different number. That is a very typical question too about this urn model. Or we can say there's some like light balls they need to be replaced, or we get a bunch of objects like a plane of book, and some book are defective, some book are not defective, and how we can choose the not defective book out, like such question. They're all about these urn models. So so after this week, we'll move into a new topic next week. I think it's about distributions. It's about discrete distributions or independent, not independent event, and conditional probability. So starting from next week, we'll explore a new topic, and I also like to recommend you to review a little bit about what we covered before, from the beginning to the urn model, and those are the basics for the probability theorem.